Well, good morning. So one of the things we've done so far is that we've developed this concept of transfer functions in general, right? We saw that the transfer functions could be taught as the response of the system to the e to the st u of t, or you could actually think about them in terms of Laplace transform if you prefer to do it that way. But one special kind of transfer function is basically the impedance or admittance. So we are going to talk about complex impedance or admittance. And we use that concept to go to the concept of synthesis. So we'll introduce the concept of synthesis. And when we start talking about it, you will see that it's a pretty broad concept, and we will definitely, you can dedicate like 2 full classes to the concept of network synthesis. So we'll just kind of like just scratch the surface barely to talk about that. But before we do that, let's talk about the complex impedance. So let's say you have a network that has 2 terminals and these 2 currents being equal. So this is a lumped circuit, and you have a V. So you have V of t and you have an I of t here, right? Now you can characterize this network as it's an LTI network in different ways, right? So one of the ways, for example, was to say V of t was generated by this, what we call the impedance operator, operating on I of t. So we had this operator in terms of P, and if it were a lumped network, then you would get basically a rational function. And what happens is that operated on this. There was another way to think about this, which is basically the Laplace transform, saying that since we know that V of t is a convolution of the system transfer function with the I of t, or in other words, you can write this as in the operator form. You can write it as V of p operating on delta of t. You remember these were the operators that generated this voltage off of a delta. Would be z of p times I of p operating on delta of t. And hence, V of p itself would have to be the product of z of p and I of p, the operators. Or you could think about it in Laplace. So this was the picture in the operator domain, the convolution converted into a multiplication. Or in Laplace domain, similarly. So V of s, if you go to the Laplace domain, or if you think about system operator, in terms of a response to an e to the st u of t, both will produce the same result, which is this result. Z of s times I of s. Right? So you could get this 2 different ways. For example, you could think that your I of t is, if your I of t, for example, is e to the st u of t, then you put it through the system, then you would get a V of t that would be z of s e to the st, a forced response. So this is the forced response only. In either case, so basically you can define this z of s, which is now a function. So z of s can be defined as V of s over I of s, or the ratio of the input and output in the case of that particular input. So you can also say this is equal to V of t over I of t for particular input where I of t is e to the st u of t. Right? They are the same thing. They are saying the same thing. But the main point to take away, no matter how you arrive at this result, is that now you have a rational function in complex variable s if you have lumped circuits. So you can have this impedance function. And similarly, you can define an admittance function, I of s over V of s. So this is the impedance, and this is the admittance. Right? So you can define these things. And the point of these things is that actually you can use them to manipulate and even synthesize things. So let's look at some of these impedance functions for various elements that we are familiar with and just refresh our memory on that. So let's start with a simple resistor. What is the impedance function? Or you can also write as 1 over G. Right? What is the impedance function, Z of S? R, right? Exactly. Z of S is R. And what is Y of S? Is 1 over R or G. Right? So that shouldn't be very surprising. The next level up is like, let's say, an inductor. What is the impedance of an inductor? Again, we've looked at this before. What is it? Well, LP, but now L is S. So it's a response to this. So P's become S's, right? So LP was correct, and then you can think about it as LS, essentially. Now it's a function. And the admittance, obviously, is going to be 1 over that by definition. So it's going to be 1 over LS. And how about a capacitor? A capacitor is going to be an impedance and admittance. Let's write the admittance first. The admittance is CS exactly, and the impedance is 1 over CS exactly, right? So they are not that surprising anyway. But now, you're also now familiar with the concept of poles and zeros, right? So if you look at the impedance function, for example, this corresponds to what? So this is the Z polar plot. How many poles, how many zeros, and where does that transfer function Z equals LS have? How many roots does it have? It has one root of the numerator, right? And that root of the numerator is at what point? At 0, at the origin, right? So this is a 0. Now, how about this guy? If you look at the impedance, because you could look at the admittance, and then it would be, I could also do admittance if you want. I've messed up my color code, but it's okay. So if I look at Y, then this is going to be a pole for Y, right? And now here, what do we have? Z of S is, for the impedance, what do I have? I have a single pole at the origin. And then, or for the Z and for the Y, I have a single 0 at the origin. You can think about it that way. Okay, so that's, again, rather trivial. Now, the next level up, a tiny bit less trivial, is now you can have combination of two of these elements. And let's see what they produce. So let's say you have an inductor and a resistor. So you have an inductor L and a resistor R. Right? What kind of, just move it here, inductor L and resistor R. So what is the impedance function here? Should be pretty straightforward, because impedances are like resistors. They add when they are in series, right? So what is the impedance of this thing? This should be trivial. R plus LS, right? And the admittance is going to be 1 over that. And how about a combination of a parallel combination of a resistor and a capacitor? What do you get from that? What is the impedance? Or let's start with the admittance. That's probably easier to calculate. What is the admittance? What form does the admittance have? Right, so it's R, or 1 over R, let's say G, right? It's G plus CS, right? And therefore, Z is 1 over G plus CS. So this should not be that surprising to you. It's a parallel combination, so the admittances add. Okay? Now, so you can see these forms kind of look similar. I mean, they're opposite of each other. But how about if you have something like this? Let's say you have an inductor in parallel with a resistor. Now, what do we get for Z of S and Y of S? So what is Y of S first? Let's calculate Y of S. So this is 1 over G. So what is Y of S? Okay, it's G plus 1 over LS, right? They're in parallel. So the admittance is add. And the admittance of this guy is 1 over LS. And the admittance of that is G. So, and there, you can also write this as 1 plus GLS over LS. And the impedance would be LS over 1 plus GLS. And then you can have another one, another alternative combination, which is what? What is the fourth combination of these one resistor and something else? Capacitor in series, exactly, right? So you have a resistor and a capacitor in series, R and C. So the impedance here, Z of S, is going to be R plus 1 over CS, which you can write it as 1 over RCS over CS. And then Y of S is going to be 1 over that, which is CS 1 plus RCS. Again, they're not that surprising by themselves. They're not that particularly profound. But and then you can also think about it in terms of poles and zeros. So if you look at the Z, for example, here, what do we have? So here we have a 0 at, and if both R and L, I mean, we are dealing with positive quant values of R and L, so where is the root of this? Where is the 0? Left half plane or right half plane? Left half, because it's negative, right? Because they are both positive. So if you set this to 0. Now, how about this one? What do we have here? We have a pole, left half to right half. Left half plane pole. Now, how about this one? What do I have here? I have a left half plane pole and a 0 at the origin, right, for the impedance. And here, what do I have? For the impedance, I have a pole at the origin and is left half plane 0. Okay, I'm going to do a couple more things just to create this. Again, we are kind of creating a catalog of things that you can generate with inductors and capacitors and resistors. And then we'll see how we can use this catalog in a second. So you have to bear with me now. I know this doesn't sound particularly profound right now. It's just we're combining these things in different combinations. But you want to come up with a way of thinking as these are really your Legos. These are your building blocks. And if you understand how they work, then you can start thinking about putting them together in a certain way to get something that's a lot more sophisticated and perform certain functions. So we want to understand our Lego blocks. The chess pieces, you want to understand what the individual moves are before you can make a combination of them. Okay, so one combination, so let's start with something like this. So now the other thing that you can do, you can have an inductor and a capacitor, right, in series, L and C. So now what is the impedance for this one? It's LS, the sum of the two impedances, plus 1 over CS, which you can write as 1 over LCS squared over CS. And Y of S, by the same token, is 1 over CS over 1 plus LCS squared. You can also kind of have the two of them in parallel, which would produce Y of S is easier to calculate. Whenever you have parallel combinations, easier to calculate the Y of S. So what you have is essentially CS plus 1 over LS, which gives you 1 plus LCS squared over LS, and then Z of S that becomes LS over 1 plus LCS squared. Okay? Is there any other combination that really matters? There are two more that are interesting, which is a three-way combination of these things. And there are more. I mean, you can keep generating more of them. But even you can see that these are made out of these elementary ones. Even these were made out of those elementary ones. So just let's, for the sake of completion, let's see what this does. So you can have an RLC parallel. Which basically, again, you can show Y of S to be CS plus G plus 1 over LS, which you can write as 1 plus LGC or GLS plus LCS squared over LS, and Z of S by the same token becomes LS over 1 plus L over R S plus LCS squared. And then the last one we are going to do here is the series combination of L, R, and C, which produces a Z of S, which is LS plus R plus 1 over CS, which generates 1 plus RCS plus LCS squared over CS, and Y of S, that's CS over 1 plus RCS plus LCS squared. Again, okay, so we had to do these things. And in terms of poles and zeros, let's quickly do that. For the Z, so here what you have for Z, what do we have? What are the poles and zeros? I have a pole at the origin for the Z, for the impedance. And what do I have? What else do I have? Okay, maybe I should let you finish writing down these things before I ask you a question. So I have a pole at the origin, and what else do I have? How many zeros do I have? 2. And where are they? On the j omega axis, right? So they're complex conjugate pairs on the j omega axis, right? Good. And then how about here? What do we have? Go ahead.
You have 2 poles on the imaginary axis.
Two complex conjugate poles on the imaginary axis and a at the origin. Yes, exactly. And since you're doing such a good job, maybe you can tell me what these are. No good deed goes unpunished, right?
A 0 on the origin.
0 at the origin, yes. So think about this. If L and R are both positive real, what is the real part of the, if they're complex conjugate pairs, what is the real part of the solution? Think about the quadratic equation. The real part of it is negative b over 2a, right? So it's going to be, the real part of it is going to be negative or positive? Negative. So where are the poles going to be?
On the left.
Left. And how are they going to be? What else can you tell me about them? They're going to be on the left half plane. Complex conjugate pairs. So they're going to be like that. Exactly. And here? Zeros, complex conjugate zeros, and a pole at the origin, right? Okay, so that's it. This is all sorts of combination. We could create more complex combinations and generate all these things and keep going forever, but we won't. So why did I do all of this? Why did I do this? So as I said, I mean, these are your building blocks. These are the elements that you can use to generate circuits and synthesize. So synthesis is so far, I mean, in courses generally, because of the nature of the way the teaching and the presentation of this material is that you take a more analytical approach in the sense that you're often given something and you're asked to analyze it. While the more useful, I mean, while that's useful, while the more useful practice is to be presented with something, some problem, and saying find a solution. So the opposite, the inverse problem is actually probably more useful from an engineering perspective, right? Because if you're an engineer, you're trying to build and create things, new solutions to existing problems. So the synthesis problem is the opposite of this thing. For example, if I tell you, I want a network, build me a network whose impedance is, I don't know, 1 plus 2s plus s cubed or s squared over s, right? if I tell you, this is a more realistic problem, because you can imagine that you're trying to make a filter, you're trying to make something that does an equalizer, some system that performs a certain function. And you say, I need a transfer function like this. The question is, how do you synthesize that? How do you make a network that does this? So that's the question. So now you can see, if I show you something simple like that, you may be able to go to the catalog that we have and say, OK, this is how I synthesize it. So which element in the catalog is a good fit, at least in terms of the forms, to this? This element, right? This has the correct form. Now, you have to see, do you have enough, can you define the R and the C and the L in such a way to get these three numbers? And you should be, because there are really 3 degrees of freedom here. And there are 3 degrees of freedom there. So your numbers may not work out to be beautiful, and they generally aren't, but you can get something that way. Right? But what if you were presented with something a little bit more general, more complex? So these are fine. If you can find it in that catalog, fine. But what if you cannot find it in that catalog? What if you cannot do this kind of synthesis? So by just looking at the catalog. So what are the ways to go about it? Can we think about certain other ways of doing it? So let's say I present to you, let me just give an example. Start with an example. So let's say I start with an example, say I want a z of s. So this is an example really, of 3s cubed plus 12s plus 1 divided by s cubed plus 6s squared plus 11s plus 6. So what do we do with this? If I say, well, you, for some reason, let's say, and then we will discuss how you come up with these things even later on. I mean, like a little bit later when you talk about Bode plots and all those things. So if you say, I want to have a certain transfer function that amplifies these frequencies and attenuates these frequencies, this is what I'm looking for. So how would you come up with a solution, a network? How do you synthesize? How do you create a network that does this? Any thoughts? Yes? So you can say do a partial fraction expansion, right? Oh, actually, I made a mistake. This is s squared. Yeah. But partial fraction. So you said do partial fraction expansion, right? So that's one way to think about it. Well, let's see where it leads us. So when you do a partial fraction expansion, so if you wanted to do a partial fraction expansion of this thing, how would we do it? You know, I have a definite advantage over you on this because I made this, so I know what it is, and you guys don't. Right? It's like factorization is always a challenge, right? That's the basis for all of the encryption. Multiplying two numbers is easy, but factoring them is not always easy. But now you also have an advantage because you know me. That's S1. Yes. But you know, I know that you know me. So I can throw you curveballs. All right. Okay, so that's s plus 1 plus s plus 2 plus s plus 3. Numerator is whatever it is. And if you do a partial fraction expansion of this thing, we're not going to spend time on that. This is going to be 1 over s plus 1, 1 over s plus 2, 1 over s plus 3. Right? That was not the part of the problem we are interested in right now. But whatever. Numerator of s. I'm not even going to copy it. So that's a partial fraction expansion, say, of this thing. So if you get this partial fraction expansion, can you synthesize this impedance? Right? How do you synthesize it? So it's basically written as sum of three impedances. How do impedances add? In what configuration? Series, right? So you have three impedances. Really, you're writing it as 1 over s plus 1 in series with 1 over s plus 2 in series with 1 over s plus 3. So this would be your network. And now we know how to synthesize these things because we have that catalog. So we've reduced it to these more essential elements, if you will. And so what is this equivalent to? So what is the first one? Let's see, somebody else, maybe. Shreya, right? Yeah, Shreya. You answered, and then, okay, what? I forgot your name, sorry. Shweta, sorry. Could you go, so think about it. Can you find one that answers this one? Resistor, capacitor in parallel. Right, that one. Okay, so you're talking about this one. Okay, that's a good one. So what is the value of the resistor and what's the value of a capacitor for this to happen? So you want this to be S plus 1. And you have one, you want this to be at 1 and 1, right? So what are the values? 1 farad, 1 ohm. So what is the next one?
The next capacitor is still 1 and the resistor is 1/2.
1/2, exactly. And then the
Again, 1 farad and
1/3 of ohms, right? Okay, so that sounds like a reasonable synthesis, right, of this thing. So let me ask you a question. Do you see any problem with this approach? Potential problem with this approach? Yes, what do you see as a potential problem with this approach?
So like you could end up having like a lot more elements than you might, like individual elements than you might like have the budget for.
That's one, yeah, so you say that you may get a lot of elements, and that may be a problem, that's true. So you're saying that there may be a more compact representation, which you're basically coming to something more interesting, which is saying that you're saying essentially that this is not unique in general. And that should make sense if you think about a synthesis problem, generally speaking, right? Because if I ask you to create a device that moves from point A to point B, there are many different ways to do that. There's more than one way. So synthesis generally is a divergent problem, which basically leads to multiple solutions. Not always, but many times, most of the time. So that's one thing, but that's not the main problem. There's an even more fundamental problem. Yes, Caitlin, right? Kathleen, sorry. Yeah.
You might have one, like the denominator's equation might be too long for you to actually find every order, might have complex roots.
So she's saying, for example, if you have complex roots. If you have complex roots, well, remember, if these are real coefficients, right, you can always write it as some of the first and second order polynomials with real coefficients. Right? So real second order polynomials with real coefficients we know how to generate in general. But okay, but you're saying that what if you have multiple roots? So what do you do about that? That's a good question. That's one question. There's even something even more basic and more fundamental about it, which I actually hid it. And this is the way things get hidden in the plain sight. Let me just try something else. What if this partial fraction expansion turned out to be this? It's possible, right? It's completely possible. It happens, right? A lot of times. What do you do in that case? Is there any way you can deal with this?
You get a negative resistor.
Well, okay, negative resistors. Yeah, easier said than done. I mean, you can generate things that produce negative resistances over a range, and you use that for some of the active synthesis. But if you were to limit yourself right now, for now, to passive synthesis, using only L's and R's and C's, negative resistances are not an option, right? You can generate negative resistances over a certain range of frequencies and operation points and things of that sort. But they are funny animals to play with, right? They're interesting. They're good. I mean, they're useful and they're fun. But right now, if we confine ourselves to this domain, can you think of this synthesis? How can we do this? Is there any way to do it? Not a straightforward way, right? And this is really what it boils down to, and that's why this is, for example, is not the partial fraction expansion may work for certain things and it may not work for certain things. Now, if you think about it fundamentally, why is that? Because when you do a partial fraction expansion of this form, you're assuming implicitly. So there may still be a network that achieves this particular, if you just multiply it out and you get a transfer function with this being negative. A network may still exist that does that. But why couldn't we get it out of partial fraction expansion? Because we implicitly made an assumption. Go ahead.
We're just assuming that every element needs to be a resistor and capacitor.
Correct. You're assuming that it's in this configuration. Right? So you are, when I write it this way, we are making an assumption implicitly. Again, we made multiple assumptions implicitly. And I kind of like played fast and loose with it, and then you went for it, right? So that's how things are sold to you, right? There are little kind of like minus signs there and here and there and things that don't work out really. But anyway, so I just basically, the assumption here is that it's in this configuration, it has this topology, which may not be true. Now, it's even more, in general, not every transfer function that I create can be synthesized at all with any configuration. And there are ways to find out what can be and what cannot be. And we are not going to go over that. But it's important for you to know that it exists and to know where to look for it. But you look at network synthesis or filter design books or things like that, or literature. Yes?
If you combine the last two terms, would it become something that is like what we're looking for?
The last two terms, this term and that term. I think you still get a negative term in the numerator, right? Because in this case, because you get an s plus 3 here and s minus 2 there. S plus 2. The first two.
No, is it like if you got s plus 3 minus s minus 2 would be 1?
No, it would be negative 1 because this would get multiplied by this, right?
Oh, I was doing like plus 1 over negative s plus 2.
Okay, you may be able to play games with this. I don't know. I haven't even thought about this, but let's see. I would actually try these first two, right? Because that would give you a 1 over s plus 1 times s plus 2, right? Plus 1 over s plus 3. And then you may be able to generate this off of what? Off of, well, there's a little problem with that still because you don't have the s in the numerator if you wanted to generate this off of this. And you can actually, obviously it has a problem because for it to be synthesized, one of the things that you need to have is that the difference in the orders for certain things cannot be more than 1. But it's more complicated than that. So this cannot be synthesized this way. Anyway, the point of this example is to tell you that the way you try to decompose this thing makes certain assumptions about how you're implementing it and the different ways to write it down. So let me show you another example of doing something like this. So let's say you have this down. Can I erase this? All right, so let me just pick another one. So now let's think about this transfer function. So z of s is 2s cubed plus 5s squared plus 6s plus 1 divided by s squared plus 2s plus 1. So what do I do with this? Well, let me show you one thing. If I actually do this, if I do a long division, what happens? Let's do a long division. So if I do a long division, so I get a, what here? What's the first term? 2s, right? So I get 2s cubed plus 4s squared plus 2s, well, minus all of that. So essentially it's going to be s squared here, 4s plus 1. So what's the next term? 1. So I get s squared plus 2s plus 1. So I get 2s. So I can write this as 2s plus 1 plus 1 over, or 2s over s squared plus 2s plus 1. So in this particular example, practically right now I'm done. But in general, if this was a little bit more complicated, what I could continue to do, I could now flip this and do another long division. Essentially, I'm writing a continuous fraction. You're familiar with continuous fractions, right? If you're not, I'll show you what I mean by that. So let's say I'm dividing this by that, because I want to write this. So let me just do the first step here. So I'm writing it as 2s plus 1 plus 1 over s squared plus 2s plus 1 divided by 2s. This is the same thing, right? But now, if I take that denominator, and now I'm also in the similar situation where this is of a higher order than the denominator. So I can repeat the same procedure. The same thing that I did with this guy, I can do now in the denominator of this guy. Right? And that's a simpler one to do, right? So because it's, I hardly need to do it, essentially. So it would be 2s plus 1 over, so this divided by that gives me 1/2, or s over 2. This divided by that gives me 1. And then I'm left with a 1 and 1 over 2s, which I can simply write as 1 over 2s. If not, this would be a larger polynomial that I would have to do this again. I would flip and do the same thing. So what's the point of doing it this way? So let's see if we can synthesize this, how we can synthesize this. So it's this impedance plus this impedance, right? So that first impedance I can write as what? What is the first impedance? It's an inductor plus, you can look at it individually, right? What is this impedance? It's an inductor of value 2 Henry. And what is the next one? A resistor of value 1 ohm. And now you're adding it to 1 over something. So if this is an impedance, this is going to be an admittance. So now I need an admittance of this value here. So what is that admittance of that value? What generates the admittance? So I want to create that admittance. Let's call this y of s. This y of s that I showed there, right? So how do I generate that admittance? Well, you can look at the individual elements. It's this. What is this in admittance? A s over 2. 1/2 farad capacitor, right? So it's a 1/2 farad capacitor plus, which in admittance domain is being in parallel or in series? Parallel, right? So what is the next element? 1 ohm or 1 Siemens resistor. And what's the last element in the admittance that's also in parallel? Inductor, 2 Henry inductors, right? So this is the network that generates that particular thing. Now, in general, you could also write, so if you have a network of this form, so let's say you have a network of this form. So you have a Z1 of S, Y2 of S, Z3 of S, Y4 of S, and so on and so forth, right? Z5 of S, Y6 of S. You can continue or not. This is called a ladder network. A ladder, for obvious reason, right? Now, this kind of decomposition is useful for creating a ladder. Why? Because if you have an impedance Z of S, you can write it as Z1 of S plus 1 over Y1 of S plus 1 over I'm sorry, y2 of s. y2 of s, 1 over z3 of s plus 1 over y4 of s plus 1 over z5 of s plus 1 over y6 of s, and so on and so forth. Now you remember continuous fractions? These are continuous fractions. And you thought they're of absolutely no use when you learned them, probably. You thought it's just some mathematical exercise. Right? And they can be, generally speaking, continuous fractions can be finite or infinite. Right? You can have this continuation. Right? So, for example, if I ask you what is 1 plus 1 over 1 plus 1 over 1 plus, etc., etc. So, you know how to calculate that one, right? It's actually pretty straightforward to calculate. How do you calculate?
The whole fraction
That's
is 12 under the first term.
Right. So if this is x, this is also x. So now you have an equation, right? X is 1 plus 1 over x. You know what the answer to this one is, right? Find it. It's an interesting thing. Okay, so you can see that form, right? So that form, that algebraic form, corresponds to this topology. This is a little bit more versatile, and this is more useful because also it kind of like lends itself more to something that's even more useful. So far we've been talking about one-port synthesis, which means that you have an impedance or admittance you're trying to create. But there's a more useful one is a two-port synthesis, where you create a system with an input and an output. So it has a port that's its input, you apply a voltage to it, for example, and it's a port that's its output, you take the output from them, like a filter or something like that. So the ladder networks lend themselves more to that and these kind of forms. And again, there's a lot more advanced ways of doing it. But in these forms, essentially, you're at the mercy of what this particular configuration allows you to do. So any mathematical form you write corresponds to certain configurations, certain topologies. And you have to see whether or not it can be realized in that form or not. But again, as I said, I don't want to go too much into too much details of this because then it would take like 2 quarters to go over all of that. But this is just to give you a feel, and you will do a couple of problem sets on this too, problems in your problem sets that would deal with this. So you will do more of these to get a sense of how this works out. Okay. Any questions? All right. If not, let's take a quick break.